Lecture 1. First, we address the problem of measure. So, the problem of measure was the length function that was in R that gave a length given length of any semi-closed open interval, lambda of that would give a length of the integral. What do we mean by length? Well, it enjoyed some good properties. First of all, if we took disjoint union, what I mean disjoint union of disjoint and countable union of intervals, which if turn out to be even again an interval, then as the notion would say, lambda of this, lambda of a comma b would turn out to be the integral or the sum of lambda of an comma bn. That is, it's same to take the length of the disjoint pieces and then sum them, or first take the sum, or first take the union of the disjoint pieces and then take the length. This is natural. This is how length was meant to be. Also, there was another beautiful property that this was invariant under translation. That is, if you translate the interval by any amount, then its length is same as that of the initial interval, because the translation of an interval is again an interval, so invoking lambda makes sense. So thing is, this length function gave us an idea of Riemann integrals. So we knew the length of length function, then we did UPFs and RPFs of a function on basis of this, and then we created Riemann integration. This was done in higher dimension, also generalized to some case for some nice looking rectangles and curves. The problem was how to generalize it even further. So the question was, let's focus in on R only. Does there exist some function mu from power set of R to infinity to R plus, actually this means greater than or equal to 0, such that it enjoys the same properties as that of the length function, but it can be done over every subset of R, such that 1. Well, first we wanted was to extend the this lambda. This is kind of a God-given length function. So mu of a comma b would have been lambda a comma b. Second, we needed it to enjoy the same properties as lambda. That is, mu of any set E plus R, that is, it should be translation invariant, should be mu E. And third, mu of disjoint union of Ens, n belongs to natural number, must be equal to summation 1 to infinity mu of n. And given such a function, we could analogously define concept of Riemann integrals on the whole of R system. So the question was to find such a function, but Vitali proved that such a function does not exist. Such a set function does not exist. And we will tell the proof that Vitali gave. So Suppose functions such like this did exist, then we will see it contradicts some of the basic fundamental things we know. Suppose such a mu did exist, then take for example close interval 0, 1 and define equivalence relation on it. So that x is related to y if y minus x belongs to q. Then take n to be all such x belongs to close interval 0, 1. So this is an equivalence relation. So there are equivalence classes. So x. So what I mean is that it would be better framed like this. So these are equivalence classes. Let's say let these be the distinct equivalence classes of this. Then take a choice function on product of this. The product is over distinct equivalence classes. Axiom of choice says that there exists a choice function in this and define n to be the image of the choice function, to be image of f. Then n properties is n enjoy. Every class of this equivalence relation has one and exactly one point in it. That is, every class intersects n at exactly one point. Okay. Now let us quickly check some properties of n. First of all, n plus r intersection n plus s equal to phi. Sorry. If r not equal to s, where r comma s belongs to rational numbers. This can be easily checked. Suppose there existed an x such that x is in both, then x plus r, then x equal to some y1 plus r, and x equal to some y2 plus r, where y1 is in n and y2 is in n. Sorry, y2 plus s. Now since s is not equal to r, y1 can't be equal to y2. So, but according to this relation, since this relation is transitive, y1 will be related to y2, and this contradicts the construction of A. So this is done. And second, close interval 0, 1. We might do this this actually doesn't make much difference. The construction is still valid. This set is subset of union r belongs to q intersection let's say -1, 2. No, not -1, 2. -1, 1 n plus r. So this is a disjoint union by the first proposition, and this is quite clear because take any x from close 0, 1, then the class of x has a representative in n, let's call it y, then x minus y equal to r. Since x and y are both in close 0, 1, mod of r is less than 1. So r is in q intersection -1, 1, and x belongs to n plus r. Yeah, and also n plus r is subset of minus 1 comma 2. This is trivial because if n is contained in closed 0 comma 1 and you're translating it by maximum 1 or minus 1 amount, so it is contained in minus 1 comma 2. Now I want you to do a quick check that from these properties it follows if mu of e if e that this is monotone, it is if e subset of f, then mu e subset of mu e is less than equal to mu f. You can check that. This is very simple. Just the technique is e union f minus e is disjoint, and this is equal to f. Just this is the method. So we get such a relation and then invoke mu3 on all the sides. So mu of close 0 comma 1 is less than equal to mu of, this is a disjoint union, n plus r less than equal to mu of minus 1 comma 2. Now since mu is an extension of the God-given length function, this means 1 is less than equal to, and since this is disjoint, this is equal to mu n plus r, but since it's translation invariant, this is just mu n, and this is less than equal to 3. Now mu n's are positive real numbers, so their sum can either go to 0 if all mu n's are 0 or diverges. Mu n greater than equal to 1 says it can't be 0, mu n less than equal to 3 says it can't be infinity. That is can't diverge. This is a contradiction. So this says it is, these three properties are mutually incoherent. So this is such a set function doesn't exist. So the question is, can't we extend this God-given set function at all? Like, can't we do somewhat better? Can't we extend to some domain, some subset of power set of R where this still exists, where such a set function exists? I mean, then we have much more sets in our disposition on which we can define a notion of integration. And that is what we will study in magic theory. So these domains are called sigma algebras. So first, few definitions. First is the definition of a semi-algebra. A semi-algebra is a space which enjoys same properties as this given this semi-open closed intervals. That is a semi-algebra. S is subset of power set of X is said to be, X is non-empty. X is everywhere which claim X will be non-empty. Is a semi-algebra on X if phi comma x belongs to S is closed under finite intersections, and if E belongs to S, E complement is finite disjoint union of elements of S. Why such a definition? Well, you can quickly see, if we take S to be all A comma B, where we use this notation, by this we means less than equal to B, less than equal to infinity. By this notation in which A and B are both minus infinity and infinity, we mean it is R, and you know what it means. So semi-open closed intervals. you can quickly see that this is actually a semi-algebra. So just verify. So this is generalization of this semi-algebra. So this is one. Second definition is that of an algebra. A subset of power set of X is an algebra on X if A is the semi-algebra and closed under complements. Quick definition: semi-algebra and closed under complements. We will give example of algebras later. And a sigma algebra, well, an algebra is not enough. We need to perform limiting processes. We need the concept of sequences. So we need countable sort of things. So that's why we define semi-algebras. M subset of power set of X is a semi-algebra, is a sigma algebra, sorry, on X if X is an algebra and closed under countable unions. Okay, before we have an example, let us find quick things. So, find if MI's, AI's, M lambda, A lambda are sigma algebras or algebras on X, then intersection M lambda or intersection A lambda is also a sigma algebra or an algebra on X. Quickly you can verify it. So suppose epsilon belongs to power set of X. It does make sense to say about M of E or E of E, by which we mean the smallest sigma algebra in power set of on X, the smallest sigma algebra on X, such that it contains epsilon. And how we will do this? Well, there is always one sigma algebra on X, right? That is the whole power set of X. That is always the sigma algebra on X. So we can just take intersections of all sigma algebras M, so that M is a sigma algebra and M epsilon is contained in M. Yeah. So that will be the smallest sigma algebra. Okay. This construction can't be done for semi-algebras because of the third problem. Okay. Now, the first lemma is given a semi-algebra is the algebra generated by S on X. Obviously, we can explicitly say what it is. It is finite disjoint union of all elements. No, sorry, finite disjoint unions of all elements of S. All possible finite disjoint unions. So how we do this? This involves a very general principle that we will use many times in measure theory. That is called a good sets principle. Okay. So first verify when S is inside S, right? And if A is an algebra containing S, well, you can easily check if algebra is closed under finite intersections, it is closed under finite unions. So if A is inside A, AS will be also inside A, since you are taking unions, right? So okay, there is an ambiguity here. Let us define this to be F first of all. I have not yet proved that this is algebra, so this notation is vague. So clearly S is inside F, and if S is inside any algebra, since F contains unions of elements of S, F is inside that algebra. So one thing is clear, F is inside the sigma algebra generated by S, and this is the smallest sigma algebra. So it is sufficient to show F itself is an algebra. If sorry, not sigma algebra. If itself is an algebra. If itself is an algebra, then AS will be contained inside F, and we are done. We are just developing the machinery now. So this is easy. First, so we need to verify two things. Psi and X belongs to A, F. This is done. S is closed under countable intersections. Sorry, finite intersections. That is, it is enough to prove that if E1, E2 belongs to F, E1 intersection E2 belongs to F. Finite proceeds by induction. So let's prove this. This is very trivial. So E1 is disjoint union n equal to 1 to KSI. E2 is disjoint union n from 1 to M S J prime, not N I J. Then E1 intersection E2 is disjoint union over for limits, necessary limits S prime J over all I and J, and since the semi-algebra is closed under finite intersection, this is also an element of F. Yeah. So the only thing left is closed under complements. So if E belongs to F, E complement belongs to F. Okay. Now, suppose this is disjoint union Si, if E is E of this form, and take the complement. So this is intersection Si complement equal to E, and Si complement is in F. Why? Because by the definition of semi-algebra, Si complement is finite disjoint union of elements of the semi-algebra. So these are inside F, and we have already shown that under finite intersection it is in F. So this implies E complement is in F. So we are done, and the proof is over. These are necessary because this develops a theoretic machinery related and will also make you accustomed with the techniques used. Okay. So we actually know what we can give an example of an algebra, that is the semi-algebra generated by the God-given S. Now, before moving to concrete examples, we use a theorem that is quite non-trivial in nature, which is called a monotone class lemma. So what is a monotone class? So monotone class is if let's call this L subset of power set of X, psi comma X belongs to L. I hope I'm not writing the definition wrong. And if L is closed under countable unions, countable increasing unions. Then L is called a monotone class. So what I mean is that if E1 subset of E2 subset of EK is in L, all of these are in L, then union EK is also in L. Now there is a quick exercise for you guys, that is, if L, the two exercises actually. One, intersection of monotone classes is also a monotone class. So it makes sense to say the smallest monotone class on a A is also a monotone class. And second, this is slightly not non-trivial, but slightly difficult than the first one. This is if L is an algebra and a monotone class, L is a sigma algebra. Okay, we may use this later, but it's an exercise for you guys. Okay. So we will given epsilon subset of X. We will use L epsilon to say the smallest monotone class generated by this. Now what we derive is the monotone class lemma that we will use later, much later actually. Monotone class lemma. We will probably use this when we prove the uniqueness of sigma finite measures, sigma by characteristic extension. Monotone class lemma, yeah. No, monotone class theorem actually, sorry. Monotone class theorem. This is if A is an algebra L of A is same as M of A. That is the sigma algebra generated by A same as the monotone class generated by A. Proof. Clearly a sigma algebra is a monotone class. So one side is trivial. The thing is the other side. So for every E in L, LA, define something called CE to be all such F belongs to LA, such that E minus F and F minus E and E intersection F. A small definition I gave wrong. This is not just countable increasing union, but also countable decreasing unions. This was a definition. Both countable increasing as well as decreasing unions. So and E intersection F belongs to F. So all such F. Clearly, first, the algebra is inside C. If E belongs to F. If E belongs to the algebra, then the algebra is also inside C, because all these elements will be in the algebra, so clearly inside it. Verify quick. If you struggle, then pause it and quickly verify it. Secondly, if E belongs to CF, if and only if F belongs to C, because these operations are somewhat commutative, And also this I will show C is a monotone class. You figure for the increasing one, I will say for the decreasing one. So if Fn decreases to F, E minus Fn will increase to E minus F. E minus Fn, sorry, Fn minus E will decrease to, as usual, Fn minus E will decrease to F minus E, and E intersection Fn will decrease to E intersection F. And since these are inside LA, and since LA is a monotone class, all this are inside LA, so F is inside C. So it's a monotone class for increasing the arrows are reversed. So C is a monotone class. So if E belongs to the algebra, then LA is contained inside CE for all E belonging to the algebra. Right. So okay. So now if T belongs to LA, then T belongs to CE for all E belongs to the algebra. For all E belongs to algebra. So, and actually not just for all E belongs to LA actually. So there's one thing that I mean to say. So LA belongs to C for all E belongs to the algebra. So if T belongs to LA, T is inside, T belongs to C for all E belongs to algebra. That means the algebra is inside LT, and this means since it is a monotone class, this means LA is contained in, sorry, not LT, this is CT. That means this is inside CT. So actually what we proved that LA is contained inside CE for all E belongs to LA. Now the proposition is done. How? So we need to show that this is closed under. So what we will show is LA is an algebra. So what we need to just show, it is closed under complements and intersections, because by this theorem, since it's an algebra and a monotone class, it will be a sigma algebra. That is the exercise that we gave. So if E comma F belongs to LA, this belongs to CE and CF. So E belongs to CF, so E intersection F is in LA. And since okay, this is done. Now if E belongs to LA, X also belongs to LA. So this belongs to CE. So X belongs to CE. So yeah, means it's a monotone class, so obviously X will belong to CE. So X minus E also belongs to LA. So it is closed under complements also. So it's a sigma algebra, and this proves the monotone class theorem. So now that the technical machinery is somewhat the introductory technical machinery is somewhat done. We can proceed to examples of sigma algebras, and we so there are very trivial examples like the smallest sigma algebra that there is just x and pi. The largest sigma algebra there is the power set x. So what we will give is the most important sigma algebra that we will deal throughout the course. Yeah, one of the most actually. That is called the Borel sigma algebra. So you can do it from an arbitrary topological space, it doesn't matter. So if x comma tau is a topological space, then the sigma algebra generated by the topology is called the Borel sigma algebra over tau. This is the definition of the Borel sigma algebra. Now, if R is given the Euclidean topology, then the Borel sigma algebra on R. This is an extremely important theorem. The Borel sigma algebra on R. You remember the God-given semi-open closed sets that were given is the sigma algebra generated by S, when S is open A comma closed, all such open A comma closed. So where this is minus infinity A, this is equal to B, that's then equal to infinity. So first we need to show that S is contained in BR. So first we need to show that S is contained inside BR. This will imply MS is contained inside BR. I mean this. So since BR since BR is a sigma algebra generated by the open sets of R under Euclidean topology, take A comma B, I mean this, A comma B plus 1 by n, and you can check that countable unions and countable intersection for a sigma algebra is the same thing because of De Morgan's theorem. I'm sorry. So take the intersection, and this is A comma B. Now, so S is inside this. So this means MS is inside here. Now, if take MS, every open set in X in R can be written as countable union of disjoint open intervals, right? So this is a theorem we have done in elementary topology. So take MS to be, so since A comma B can be written as A comma B minus 1 by n for some suitable n union, n belongs to some, for some greater than equal to some n naught. So this means A comma B is also in MS. So all since every open set is a disjoint intersection of open intervals, since all open intervals in SS, the topology is inside SS, so the Borel sigma algebra is also inside SS. Hence we are done. Now, what we define, the penultimate topic is the product sigma algebra, and we do it for just for two finite cases. So the product sigma algebra, suppose you are given two measure spaces, so given X and a sigma algebra is called a measured space, measurable space probably, and Y comma M prime. So Y is X spaces at A minus 0, measure space on there. So these are called measurable spaces. So we want to define a measure space on this. So for those who know the concept of measurability, so this is, we intend to define the smallest sigma algebra so that the projection operators are measurable. So define M tensor M prime. Those who don't know that will know soon enough. M tension M prime is, so given the projection map P1 and P2 is the sigma algebra on X cross Y generated by P1 inverse E union, I mean all such elements of the form P1 inverse E, this set P1 inverse E belongs to M union P2 inverse F belongs to M prime. So this is the sigma algebra that we find. And okay, so this is sigma algebra and X cross Y. What we will show is a very remarkable theorem is that Borel sigma R2 is same as BR tensor BR. That is, so this is that what we will prove. So I mean this is wrong, this is not correct. I mean we have to write, this makes no sense actually. This is P1 inverse E product P2 inverse F, E belongs to M, F belongs to M. Now it's okay. Now so these two are sigma algebras on R2 and we need to show they are the same. So first of all, since for now Borel sigma algebra on R2 is generated by all open sets on R2, and for R2 actually Rn you can show that actually any locally path connected separable matrix, the separable matrix space, you can probably show that it is disjoint union of its open connected disjoint union of open connected path intervals. Okay, I mean this is, that is countable union of countable union of connected components, countable union of its connected components. You can show this if and only if it is locally path connected and separable. If it is locally path connected and separable, probably, yeah. So the first trick is to show that these A1 comma B1 all open rectangles form a basis of the topology for on R. So I won't tell, I will just give a hint how to show this. So all norms on R2 are equivalent, right? So yeah, no, that won't give a Google method. So you have to show that any open ball, so the basis of R2, basis of the topology on Euclidean topology R2 are the open balls. So If you can show that they are countable union of open rectangles, then we are somewhat. That's the first step that we need to show. So an easy method, well, there are easy methods. That is, most easy method is R2 with Euclidean topology and R2 with this norm, that is max of norm x comma norm y. So if we take this, since all norms are equivalent on Rn, if you take the identity map, so this is open, these rectangles are open, so no, this won't work. To show that this is the basis of R2, right? So what we need to show that any open ball can be written as countable can be expressed as countable union of rectangles. So this is easy. So take any open balls, you know R2 is separable, right? So take the one with the rational coordinates. So given a open ball in R2, so if B is an open ball in R2 of any in radius R probably. Take all coordinates x comma y in BR such that x is rational, y is rational. Take all those 1 by n's such that x plus 1 by n comma x minus 1 by n cross y plus 1 by n, y minus 1 by n is contained in BR. This can be done. You can think it of geometrically, and you can think it of the form that inside a ball is open. So it is open under Euclidean topology, it is open under this topology, and under this topology balls are actually rectangles. So from there you can show it. So there exists 1 by n's. So take all such n's such that these happen, and take union of all these rectangles, and you can easily see that this, since x comma y it is a dense set, so you can see from there it forms that these rectangles, the union of these rectangles is BR. So it's a rough sketch. So this is the idea. So you take these rectangles, and the converse idea, so these rectangle countable union of these rectangles, so these rectangles are in BR cross R, so countable union of these will be there. So every open ball is in BR tensor R, BR, and hence the entire topology is there. So one side is done. This is a very rough idea. You are invited to put all the details. You are recommended to put all the details. BR tensor BR, and conversely, so you can show that these open rectangles, so it can be shown that if these actually generate BR tensor BR, so this can be shown. So it's not a very difficult step, but okay, if this cannot be shown, clearly this can be shown, that since A1 comma B1 this generates Borel sigma algebra of R. Well, this is not exactly obvious, but this, so an exercise is this generates BR tensor BR. Since A1 comma B, so A1 comma B1 tensor generate. So what I mean is that S crosses M of this generates BR tensor BR. So exactly same method as I showed, that S generates BR tensor BR. So, and from here it will imply, not out trivially, this is inside Br tensor Br, and since these are, so equivalently you can show that these generate actually these sets, that these rectangles also generate Br tensor Br, because these generate these and these generate this. It's analogous method as before. And since these are open, these are inside this topology, so the converse is shown, that Br tensor Br is contained inside Br2. This is a bit vague, but you are invited to put all the details. You can follow. I will give a reference of a book from where I am mainly following stuff. So this is the idea of the proof, but it's a bit vague. It's exactly that idea, but I'm not filling out the details. Okay. So you can complete by induction that Brn is tensor of Br.